Breaking down giants and building new icons, welcome to the exciting world of demolition, construction, and bridge assembly. At the Osmanghazi Bridge project, concrete placement tests were carried out to evaluate the workability and ease of placement of fresh concrete. These tests are essential to ensure that the concrete can be properly placed on site and achieve the required strength and durability. Among the most widely used methods, the slump test measures the consistency and workability of fresh concrete, while the compaction factor test assesses its compactability. The V-funnel test evaluates flowability and placement characteristics, and the flow table test measures the spreading behavior within the formwork. Additionally, the temperature of fresh concrete is carefully monitored, as it significantly affects performance during placement. To ensure accuracy, samples are always taken from a homogeneous mix that truly represents the batch. By conducting these placement tests, engineers confirm that the concrete used at the Osmanghazi Bridge could be correctly placed and compacted, guaranteeing structural safety and long-term reliability. A CAT 349E excavator feeding a Sandvik UJ 540 mobile crusher, demonstrating an efficient material handling process. The excavator loads rocks and soil into the large hopper, where the feeder pre-screens the material. Even though the feed contains a considerable amount of fines, the screening system ensures that the material remains clean and suitable for crushing. The hopper in operation has around 4,000 working hours, yet its wearing plates are still in good condition, highlighting the durability of the design. However, the nose of the feeder shows signs of wear, becoming thinner due to constant contact with abrasive rock. Operating at a capacity of 400 tons per hour, the machine has already processed approximately 600,000 tons of rock using a single set of original liners. This performance demonstrates the robustness and reliability of the equipment in demanding quarry environments. The tunnel boring machine, TBM, featured in this project represents one of the most advanced methods of underground excavation. This particular TBM achieved its breakthrough for Tunnel A of the East Side Access project in Long Island City, Queens, on December 26, 2011, successfully reaching its receiving pit. Tunnel A will serve as a vital passage for westbound trains entering the Long Island Railroad's new Grand Central Terminal, significantly improving connectivity for commuters. The machine began its operation on August 10, 2011, and worked relentlessly through challenging geological conditions, including hard rock, boulders, gravel, sand, and clay. Its precise engineering enabled continuous progress underground, ensuring both safety and efficiency in excavation. Following its breakthrough, the TBM will be carefully disassembled, transported on flatbed trucks to 29 to 76 Northern Boulevard in Long Island City, and reassembled to begin work on Tunnel D. This second tunnel will provide an eastbound route for trains departing from the new Grand Central Terminal. Once the East Side Access project is complete, 4 new tunnels will connect directly to Grand Central, representing a major achievement in urban infrastructure. The TBM stands as a symbol of technological innovation, efficiency, and the future of modern transportation. The Osmanghazi Bridge, also known as the Izmit Bay Crossing, is one of Turkey's most iconic infrastructure projects and features a remarkable deck installation process. As a suspension bridge with a main span of 1,550 meters, it uses a steel orthotropic deck comprised of prefabricated box segments. These deck units, measuring 18.6 meters wide and with lengths of 40 meters, 19.2 meters, and 23 meters, were manufactured off-site under strict quality control to ensure precision. Once completed, the segments were carefully transported by ship to the construction site. Multiple steel boxes were stacked and carried across the bay, optimizing both efficiency and safety. At the site, heavy lifting equipment played a crucial role. A floating crane hoisted each segment from the ship and positioned it onto suspension hangers connected to the main cable, ensuring perfect alignment for structural integrity. The project also set a milestone in engineering with the world's largest heavy lifting operation. Two massive viaduct sections, measuring 127 meters and 133 meters, were lifted with weights of 302, 600 tons respectively. This record-breaking achievement highlighted both the complexity and the advanced technology employed in the Osmanghazi Bridge deck installation. The Hollandse Brug, an essential link between Amsterdam and Schiphol, recently underwent a remarkable construction phase involving the installation of 8 precast concrete bridge piers. Each pier weighed up to 64 tons, which required advanced engineering methods, precise planning, and specialized lifting equipment. This operation not only demonstrated technical expertise but also ensured the long-term stability and durability of the bridge. To begin with, the process started at the fabrication plant, where the massive concrete piers were manufactured with exact dimensions and reinforced with steel to meet design requirements. Once completed, the piers were carefully transported to the construction site. Because of their extraordinary weight, heavy-duty transport vehicles with multi-axle trailers were used. Moreover, logistics planning was critical, since the delivery had to avoid disrupting traffic while ensuring safety along the route. Once the components arrived on site, the next step was to prepare the installation area. Before lifting could commence, the ground and foundation had to be reinforced and checked for load-bearing capacity. This preparation stage was essential, as even a small deviation could compromise the alignment of the bridge deck. Subsequently, cranes with exceptional lifting capacity were brought in to hoist the piers into place. Each pier was slowly raised and maneuvered with great care, while engineers monitored its movement from multiple angles. Furthermore, temporary supports were positioned to stabilize the structure during placement. Once lowered into its designated position, the pier was adjusted with millimeter precision until verticality and alignment were perfectly achieved. Afterward, the focus shifted to securing the piers permanently. Connections between the piers and the foundation were strengthened with reinforcing bars and additional concrete pouring. At the same time, joints were sealed to create a continuous and durable load-bearing system. During this phase, strict quality control procedures were carried out to test the strength of the concrete, the reliability of reinforcement, and the stability of the entire structure. In the following stage, inspection and verification played a crucial role. Engineers conducted thorough checks to confirm that each pier stood upright within tolerance levels and could withstand both static and dynamic loads. Measurements were compared with design data, while safety tests simulated real conditions. Only after these verifications were the piers officially approved for integration with the bridge deck. Finally, the successful installation of the 8 concrete piers marked an important milestone in the Hollandse Brug project. The combination of heavy lifting technology, precise surveying, and effective teamwork ensured that the operation was completed efficiently and safely. Moreover, the achievement reflected the high level of coordination among designers, builders, crane operators, and supervisors. In conclusion, the placement of 8 concrete bridge piers, each weighing up to 64 tons at Hollandse Brug, highlighted both the challenges and the excellence of modern bridge construction. Thanks to careful preparation, advanced equipment, and rigorous quality control, the bridge now rests on a foundation that guarantees stability for decades to come. By the end of 2016, Scotland's most ambitious transport infrastructure project in a generation, the Queen's Ferry Crossing, was approaching completion. This new bridge, the third to cross the Firth of Forth, was designed to link the outskirts of Edinburgh with Dunfermline in Fife. Stretching across 22 kilometers of new road network, the bridge and its approaches represented not only an engineering challenge but also a symbol of modern Scotland. By December, 94% of the work was finished, with the opening scheduled for May 2017. What remained were the final deck concrete pours, road surfacing, and installation of the mechanical and electrical systems. To begin with, one of the most striking achievements of 2016 was the installation of the stay cables. Cable installation is always an extremely wind-sensitive operation, requiring teams of workers to feed strands into massive pipes up to 200 meters above sea level. Over the year, 200 stay cables were successfully installed, reaching a total combined length of 50 kilometers, enough to stretch from the bridge to the city of St. Andrews if laid flat. Each stay cable contained up to 109 individual strands, and in total almost 4,000 kilometers of steel strand were installed during the year. To put this in perspective, that length could reach all the way from the Queen's Ferry Crossing to Cairo. Alongside the cable work, the deck of the bridge advanced rapidly. By the close of 2016, the bridge deck was largely complete, with only 2 more lifts required in early 2017. During the year, 83 deck sections, together weighing over 60,000 tons, were carefully lifted into place. Each lift was a slow, highly methodical process, heavily dependent on favorable weather conditions. The operation became even more complex when sections had to be fitted near piers, where precision alignment was critical. One of the most technically demanding operations occurred in May 2016 during the Pier S1 deck lift. Later in October and November, engineers undertook the final closures between the deck fans at the towers. This required fitting hundreds of tons of steel and concrete into gaps as narrow as 6 meters. Fine adjustments of cable tension were necessary for alignment, and powerful hydraulic jacks pulled sections back by 60 centimeters to create the necessary space. These moments marked important milestones. First, the closure between the center and south tower decks in October, followed by the closure between the center and north tower decks in November. Notably, the center tower deck fan achieved a place in the Guinness Book of World Records in October 2016. At 644 meters in length, it became the longest freestanding balanced cantilever structure ever built. Although it held this record for only 42 days before the center and south tower decks were joined, it demonstrated the extraordinary feats of engineering accomplished during the year. Meanwhile, the viaducts that formed the approaches to the main bridge also saw major advances. The North Approach Viaduct was launched in February and March 2016. This operation was one of the most challenging of its type ever attempted, as the 221-meter-long, 6,000-ton structure was gradually pulled out over 2 piers. The process was deliberately slow, advancing at a maximum speed of 6 meters per hour, and took around 4 weeks to complete. Particularly remarkable was the maneuver to pivot the structure on Pier N2, raising its front end by 4 meters to clear Pier N1 and allowing perfect alignment with the rest of the bridge. By the end of the year, the concrete deck on the North Approach Viaduct was fully complete, while the longer South Approach Viaduct had reached about 90% completion. Equally important were the new road networks that would connect the bridge to Scotland's motorway system. North and south of the Forth, earthworks for both motorways and side roads were completed, while 3.5 kilometers of road surfacing and 8 kilometers of drainage pipes were laid. Engineers applied 500 square meters of waterproofing spray and erected 14 overhead gantries for traffic management. In addition, 44,000 trees were planted as part of landscaping and environmental mitigation efforts. Throughout 2016, the public closely followed progress, often marveling at the sight of the deck section suspended high above the water. Many spectators wondered whether the deck ends, swaying in the wind, would ever meet. Engineers explained that the temporary freestanding deck fans were influenced by multiple forces, particularly strong winds and the sag caused by the weight of each new segment, which could dip the deck by up to 4 meters the height of a double-decker bus. In conclusion, by the end of 2016, the Queen's Ferry Crossing stood as a near-finished monument to modern engineering. With 94% of the work complete, including record-breaking deck construction, the successful launch of the North Approach Viaduct, and extensive progress on roadworks, the bridge was nearly ready to open. The final major concrete pour on the Queen's Ferry Crossing marked one of the most significant milestones in the delivery of Scotland's most ambitious infrastructure project in recent decades. This stage completed the bridge deck, bringing together years of intensive planning, engineering, and construction effort into a tangible achievement. The operation involved careful coordination, as the concrete had to be poured in precise stages to achieve uniformity and strength across the entire span. This task was crucial not only to the structural integrity of the deck, but also to ensuring that the bridge would meet the rigorous safety and durability standards required for such a vital crossing. Once the final pour was completed, attention shifted towards the finishing works that would transform the bridge from a structural framework into a fully operational transport link. These activities included installing road surfacing, barriers, lighting, drainage systems, and other essential fittings. Each task was undertaken with meticulous attention to detail, since the bridge was expected to carry tens of thousands of vehicles daily and needed to provide long-term resilience against the challenging weather conditions of the Firth of Forth. This concrete pour and subsequent finishing activities represented more than just technical accomplishments. They signified the conclusion of the deck's construction, which had been one of the most complex and demanding aspects of the project. With the deck completed and finishing works advancing, the Queens Ferry Crossing moved closer to its official opening in 2017. The entire effort formed part of the wider Forth Replacement Crossing project, which included new road connections on both the north and south approaches. Together, these developments safeguarded a critical transport artery, maintaining the economic lifeline between Edinburgh, Fife, and beyond. In essence, the final concrete pour not only completed the deck, but also symbolized the bridge's transition from construction site to national landmark. The installation of the Malahide pedestrian bridge marked a significant step in improving local accessibility and safety. Before the actual assembly could begin, the temporary path that had been used during the construction phase was carefully dismantled and removed. This ensured that the site was fully cleared and ready to accommodate the bridge structure. Once the access route was open, preparations were made to receive the prefabricated bridge sections. These sections, which had been manufactured off-site under controlled conditions, were delivered to Malahide using specialized transport vehicles. Their arrival marked the beginning of the installation process. Each section was carefully positioned with the assistance of heavy lifting equipment, ensuring accurate alignment with the foundations already prepared on both sides of the crossing. The process required precise coordination between engineers, crane operators, and site workers to guarantee both efficiency and safety. As the sections were joined together, crews worked to secure all connections and stabilize the bridge deck. Final adjustments were then made to ensure a seamless fit and proper load distribution. Once the structure was in place, finishing works such as railing installation and surface treatment were completed. The result was a modern pedestrian bridge that not only provides a safe crossing but also enhances the visual character of the Malahide area. The installation of the propylene tower at Wanhua Industrial Park in Yantai, China, marked a remarkable demonstration of heavy lifting technology. For this task, the XGC 88,000 crawler crane, manufactured by XCMG, was deployed as the main lifting equipment. With a rated lifting capacity of 4,000 tons, the XGC 88,000 is recognized as the largest and most powerful crawler crane in the world, designed to handle some of the most challenging lifting projects in the petrochemical and energy sectors. The propylene tower itself presented an immense challenge. Measuring 118 meters in height, 14.4 meters in diameter, and weighing 680 tons, it required extraordinary lifting precision and stability. To meet these demands, the XGC 88000 was configured with a 108-meter heavy boom in combination with a 33-meter fixed jib, allowing the crane to reach the required height and safely maneuver the massive structure into position. In addition to the main crane, a newly developed 1,000-ton XGW 1100 crawler crane was used in coordination with a crawler transporter. This secondary crane provided critical assistance in adjusting and stabilizing the tower during the final stages of positioning, ensuring accuracy and safety throughout the complex lifting process. The successful hoisting of the propylene tower not only highlighted the technical capabilities of the XGC 88000, but also underscored China's advancements in heavy lift engineering. With a maximum lifting moment of about 9,000 tons, the crane has set new benchmarks for large-scale construction projects worldwide. Its deployment at Wanhua Industrial Park represents a significant achievement in the integration of cutting-edge lifting machinery with industrial development, showcasing how the world's strongest crawler crane can accomplish extraordinary engineering feats. Hanshin. The installation of pipe culverts begins with a thorough inspection of all delivered pipes to ensure that there are no cracks, dents, spalls, or coating damage. At the same time, the lifting equipment provided by the contractor must be checked, making sure that the rated capacities meet the manufacturer's specifications. Each day before installation, all equipment is visually reviewed, and any worn or damaged hardware must be replaced. Before excavation, an embankment may be constructed if required, ensuring proper elevation. Utilities marked on the site must be identified, and the trench is excavated to the correct dimensions, with slopes laid back appropriately for safety. The trench bottom is then compacted using approved rollers or compactors, and if unstable areas appear, they are excavated, dried, and replaced with suitable material. A proper bedding layer is placed 6 inches deep with aggregate, depending on the pipe type. Pipe placement follows, with bells or grooves positioned upgrade and spigot ends fully inserted into hubs. Alignment and grade are controlled using string lines or lasers. Joints are sealed according to material type: concrete pipes with caulking and geotextile wrapping, metal pipes with bands and geotextile, and thermoplastic pipes with preformed gaskets. The Malahide. Once the pipes are in place, backfilling begins. Aggregate is placed along the sides of the pipe in 4-inch compacted lifts using hand-operated equipment. Proper lateral support is ensured, especially for metal and thermoplastic pipes. At the crown of the pipe, uncompacted material is maintained 1 foot for metal and thermoplastic pipes and 2 feet for concrete pipes. Backfilling continues in layers, with compaction performed according to the type of equipment used. Finally, All excavation, placement, and backfill operations are documented to verify compliance with specifications, ensuring a durable and properly installed pipe system.